Yeah, in the yesterday's lecture, we have seen the Euler-Lagrange equation in which the Lagrangian has to be identified. Only then we can solve some problem. So that was the explanation that we were trying to see in the last class. And our conclusion is that even though infinitely many possibilities are there for choosing the Lagrangian, the one that is suitable to generate the Newtonian equation is given by T minus V. So that is what we have seen in the last class, and that result is actually obtained by making the reverse calculation starting from the Newton's equation of motion, and by doing the reverse calculation by taking simple problems, people have identified that the possible Lagrangian that can work successfully is given by the kinetic energy minus potential energy. So that was the main conclusion that we have done in the last class. In addition to that, we have also seen how to express the kinetic energy and potential energy in terms of the time derivatives, because we don't want to have velocity, but instead we will have to write x dot y dot, or in terms of polar coordinates, for example, r dot, theta dot, etc. So once you have these expressions, it is quite easy to start with any problem. And today we will take one or two problems in this particular list. Already I have written down some of the standard problems, which will give you a good insight into how to work with the Euler-Lagrange equations. Okay, so these are the standard problems, and not only that, because it is standard problems, it also gives you a very good insight into how to apply the Euler-Lagrange equation and how to choose the coordinates, where to fix the zero of the potential energy. So these are the important points. Fixing the zero of the potential energy is very important, because you have to write down potential energy for the system, and that is arbitrary. You can choose any level as the zero of the potential energy. So depending on that, your equations will be different, which means that if you are choosing one level as zero as the potential energy, and your neighbor means the person who is sitting near to you in the examination hall, he will be choosing a different level as the zero of potential energy, and then you can always do the calculation. The equation will look slightly different, because the zero levels have been chosen as different levels by the two different students who are sitting near and near. So therefore, because of this reason, you should remember that the equation will not always look identical for every person. Okay, it will look identical only if you choose same zero of the potential energy. So this is very important. So therefore, you have to first of all draw a proper coordinate system, and then draw a proper diagram. So drawing the diagram and then drawing the coordinate system, identifying the zero of the potential energy, that solves almost 50% of the problem. The rest of the thing is only substituting into an equation and then obtaining it. It's only a matter of calculating partial derivatives and then d by dt of that. So that is quite simple for you. So what is the major focus that you will have to pay attention in any of the problems that we are going to solve is the two things. One is that you'll have to draw a proper diagram, neat diagram, and then identify the coordinates system that you are planning to use. It can be any one of the coordinate systems, polar or rectangular. So you will be choosing one of them properly, identify where would be the origin, and then zero of the potential energy. That's all. And in addition to that, the next difficulty or the next attention that you will have to pay is to find out the equation of constraint. So these are the things. Once this is identified, the rest of the thing is only simplification of equation, which is going to be very simple. So where is difficulty and where is simple, I have already outlined. Okay, the first portion you will have to pay attention in drawing appropriate diagram. So I am once again repeating, drawing neat diagram and then identifying the variables, etc. They are very important. For that purpose, let us first choose the problems A and B. Let us first start with this one, namely the Atwood's problem. And then we will go on to the simple pendulum problem. And the advantage is that even though the simple pendulum problem may appear to be simple, it lays the foundation for learning the spherical pendulum, conical pendulum, and double pendulum. They are just modifications of them. Spherical pendulum means you are just extending the two-dimensional oscillation to three-dimensional oscillation. You are allowing the pendulum to oscillate anywhere on the surface of the sphere. So that means when the bob is hanging, you are not going to use a thread, but instead you are going to use a light rod. Light rod means the rod itself should not have mass. It should have very little mass that should be negligible in comparison to the bob. And then if you are going to oscillate that, you are going to allow the oscillation not only within the plane, but it can also go anywhere in the circular region, not in a plane, and therefore it takes a spherical surface. It can go anywhere on the surface of the sphere. That is called a spherical pendulum. Conical pendulum, you can easily imagine. You are not allowing the bob to pass through all possible points on the sphere, but you are going to restrict to lie within a cone. So once you put the theta axis in the coordinate system, namely the cylindrical coordinate system, you allow for some range of theta. Only then it will be a cone. If you allow all possible angles, then it will become sphere. So the difference between sphere and the cone you'll have to observe. Cone can be, you can always fit a cone inside a sphere, isn't it? So that is what you have to imagine. You draw a sphere, and can you bring a cone and fit it there? You bring the center of the sphere and then take the apex of the cone, and then you try to fit it. It will fit nicely. So our conclusion is that conical pendulum will be a special case of the spherical pendulum. Mathematically, it becomes a restricted one, and the simple pendulum is restricted to a plane. So therefore, simple pendulum lays the foundation to move further into next level difficulties by increasing the number of dimensions. That is one thing. Second thing is the equation of restriction or equation of constraint will change. For spherical pendulum, you'll have to use the equation of sphere. For conical pendulum, you'll have to use the equation of cone. These are the equation of constraint you'll be using. And in the case of the simple pendulum, you already know what is the equation of constraint. So this is how the small changes will be there from one problem to other problem. And therefore, our aim in this particular class is, therefore, we will take one example and go in detail how each step is done. Okay, certain things may look too simple, but just because it is simple, if you neglect it now, when you are going to attempt a next level difficult problem, you can't do anything. So therefore, starting with a simple pendulum and learning in detail is very important, so that similar steps can be applied when you are moving to the next level problem, such as the F and G. F and G is the thin cylinder. You can read this. Probably I will show it on a white color cursor. Yeah, so now the cursor is coming. So this F and G is a thin cylinder rolling on a large cylinder. What is the meaning? You'll have to first of all imagine. You have to use your imagination power and see what do you mean by large cylinder. Is something like a drum. You take a big drum. Okay, the radius is quite large, something like 1 or 2 meters. Okay, bigger drum that you have. Thin cylinder means something like a pencil. You know, the outer surface of the pencil should not be hexagonal. Okay, it should be smooth one, which means cylindrical in shape, or something like a chalk piece. Okay, so that is called a thin cylinder. If you keep a thin cylinder on top of a very large cylinder, then you know that it will roll down. So when it is rolling down, it will come down to a certain level, and after that it will get detached from the large cylinder and then simply fall down. But forget about the free fall situation. Until it is maintaining contact with the larger cylinder, it will keep rolling. Okay, slipping condition you have to neglect. Slipping should be avoided, and then assume that there is a pure rolling, and then the thin cylinder rolls and then slowly comes down on a larger cylinder. That's all. That's the statement of the problem. And then in this particular situation, how will you determine the equation of motion? So in all, and then rotating hoop. Hoop means something like a circular ring with a little amount of thickness. Okay, that is called hoop. And when the hoop is rotating, and then you can attach a bead, etc. You can do some additional difficulties to the problem. When a hoop is rotating, you can always determine the equation of motion of the attached mass to that. So these are next level problems where you'll have to think about the nature of the constraint, and then you'll have to bring into moment of inertia into picture. So as and when required, you'll have to add some little complexity to the problem. So if you learn these problems A to G here, in general, you'll get a good idea about any problem that is given to you. You will be in a position to successfully deal with the system, because these examples give all possible examples, namely Cartesian is there, spherical system is there. You can always use a cylindrical system for the case of conical pendulum, and again thin cylinder rolling on means you'll have to use a cylindrical polar coordinate system. And hoop rotation is basically it's a cylinder. Hoop is a circular ring, so you can choose a polar coordinate system. So this particular example set A to G provides you ample experience to deal with various coordinate systems, and then identifying the required variables, namely the number of degrees of freedom, and then it gives you a good exercise to have a confidence in solving the Lagrangian problems. So this is the aim of our class now. Let us therefore start with the Atwood machine. And then here I have written two things. This is important. The solution of the Atwood machine can be done with the inclusion of the moment of inertia. That's what I have written. You can also solve the problem by neglecting the moment of inertia of the system. So we will be getting two different answers if you include and if you don't include. So let us therefore see how we can include and how we can exclude that. So let me therefore go to the Atwood machine case, which is nothing but it is two masses connected to a pulley. If you take two masses and connected to a pulley, that is called the simplest Atwood machine. You can always complicate the Atwood machine by adding additional pulley systems to that. Okay, so let us therefore start with the problem A, first problem, and let me therefore draw a suitable diagram for that. So this is the simplest diagram that we can draw. Here we will have to consider that one of the masses is larger than the another mass. Okay, otherwise if you release the system, then there won't be any dynamics. If two masses are of equal mass, then there won't be any dynamics. So let us assume that one of the masses will be the larger than the another mass. That is one thing. Second thing is this particular pulley that you will have to consider as frictionless. Why you have to consider it as frictionless is if the friction is there, you know that it is a non-conservative force, and which means that you do not have the equation for that. If you don't have the equation for that, then it becomes non-holonomic, and therefore the system may not be integrable. So you see the importance of the assumption frictionless. You can have friction, but you should know the corresponding equation of what amount of friction is going on. But in general, we will not be knowing. Therefore, we will make an assumption that it is frictionless by experimentally we will say that we are going to lubricate the pulley, and then we are going to have ball bearing, etc. And we are going to minimize the friction and approaching zero. That is what is the assumption that we are going to make, which is an important assumption. The second assumption that we are going to make is that the wire that you are going to use for hanging the two masses should be inextensible. So that is another assumption. This assumption, why do you want to make, is that if it is extendable wire is something like elastic wire. You can imagine an elastic wire. Take an elastic wire and then attach two masses at the two end. That is, I am talking about this particular wire that is hanging. If it is elastic, you know what will happen. It itself will start oscillating like vertically. It will oscillate like a simple harmonic motion, and that will generate additional accelerations in up direction and down direction, and then complicate everything. So you should know why we are making such kind of assumption. If there are assumptions are there, then the problem we can write down corresponding kinetic and potential energies. If you are bringing spring into picture, then it will be difficult. You'll have to then bring what is the spring constant of the system, and correspondingly you should not. You should also know what amount of the elongation will be there. See, the difficulties are not simple difficulties. It will complicate too much. If a particular spring is extending, you should know by what length the elastic wire will elongate by an applied force or applied mass. If that is not known to you, you can't calculate this, because length of the wire is very important. So let me therefore explain what is meant by length of the wire. I am now putting a dot here. So this is the starting point, right? So from here, and then you come all the way like this, and then you pass through this particular pulley, that is this thread or wire, and then come like this, and then you attach here. So that is the starting point, that is an ending point. starting point to the ending point will be the length of the wire. That is the total length of the wire. So this should be clear to you. If that is not clear, then calculation will be difficult. So in this case, we can now, we have to write down some expression. Okay, we can say that the total length is L. So that is fine. But we need to write down what is the total length, because when you are allowing the system to move, let us say that the mass M1 is going up and M2 is coming down, then you know that one side you will be having a smaller length and the other side you have a larger length. So the total length you will have to calculate and write down what this L will be. That should be done so that we can do the calculation. Now before this, I have used one particular, let us do that. But before that, while explaining this kind of assumption like frictionless and inextendable condition, I have used one important word, what is known as, when the system is non-holonomic, then the equation of motions will be non-integrable. This word I have used. Okay, so let me explain therefore that one. So this terminology, non-integrable, is something very important, and it will be frequently used in the dynamical systems theory. So non-integrable is quite simple, not a complicated complicated term, but the meaning should be clear to you. What do you mean by integrability of a dynamical system? So that if that statement is clear, then you can always understand what is meant by non-integrable system. Integrable refers to the integrability of a differential equation. That is what we mean to say. If I have any equation like this, y double prime plus, let us say, k square y equal to 0, you know that this is a differential equation. And then immediately you write down that the solution is, you do some simple thing and then write down that the solutions are looking like a cos kx plus b sin kx. This is what you do routinely, and you know that this is the solution. Now, what is the conclusion from here is that we are going to now say that this particular differential equation is integrable. So this word is what I am trying to explain. You already know what it is. You take a differential equation, solve it. If you are able to successfully solve, you get the solution. And you say that, okay, I got the solution. This is a general solution because constants are there, a and b. That's fine. But what is the conclusion finally is that the given differential equation is integrable. That is a conclusion. If a given, suppose if you have another complicated differential equation, and suppose if you are unable to solve it, you try all possible different methods and you are unable to solve, okay, then we make a conclusion that that particular differential equation is non-integrable, which means that the solution cannot be found by whatever techniques that are known to you. Okay, probably it may be this situation where a new discovery has to be made. That kind of situation, we do not know. That we means not you and me only, but the set of all people who all work in the mathematics. Okay, none of them know how to solve it. That is what I mean to say. You means not an individual. Okay, the entire set of people who work in mathematics, none of them know how to solve a particular differential equation. Then it means the inability to integrate. That's what we mean to say. The differential equation is so complicated that we are unable to integrate it. Integrating a differential equation is what is the solution. So that is what is the important point. If you have a second order differential equation, basically you are performing two integrations to get the solution. But in the theory of the differential equation, you don't perform an integral like this. You don't do an integral and then get the answer. You don't do it. But in an indirect manner, this is what is happening. You may be following some procedure, but that procedure is actually performing the integration, and that is giving you the solution. Therefore, integrability of a differential equation means the ability to solve the differential equation. That's the meaning. And when our dynamical system is non-holonomic, when it will become non-holonomic, you do not know what is the friction. You don't have an equation at all. Then how will you substitute and how will you deal with the equation? And therefore, when the differential equation itself you are unable to write properly, then how can you search for its solution? And therefore, we can't ask what is the solution for such a problem, and we therefore say that the dynamical system is non-integrable. So this is called integrability of a dynamical system, and the word is, this particular technical word will be frequently used. So that is why I have explained this one. Okay, coming to the original problem, let us therefore start with this. We have the diagram like this. Now we will have to identify the coordinate system, and then we will write down the appropriate variables. So let me therefore draw an x-axis corresponding to this. Let us take the center. You can take anywhere. This is the place where the interesting point comes into picture. And now I am going to choose that the x-axis will be the one that I am drawing in the yellow color. But it is not necessary that you have to draw the x-axis here. You can draw anywhere. That means you can draw below. You can also draw above. That means it is the choice of the coordinate system. It is arbitrary. You have the freedom to choose it. But whatever be the coordinate that you are going to choose, your equation will look different every time. If I change the x-axis to a different place, all my equations will look different, but finally my answer will be same. Final answer means the equation of motion. So that is the interesting thing. So that is these equations are ultimately leading to the solution which are independent of coordinates or coordinate system. You can use any coordinate system. Ultimate solution won't depend on the coordinate system. Okay, let us first take this particular situation where I'm going to choose this, the center of the pulley itself as the origin. In that case, we can draw like this. So let me therefore draw the y-axis also corresponding to this, probably like this. And therefore, once you have this, we can then identify that this will be the x-axis and that will be the y-axis. So once you have x and y axis, now it is a proper time to write down what are the length of the wire, or we can say that the distance of the mass from the reference x-axis. Okay, the reference x-axis is very important. The word reference, why I am using, you can simply say x-axis. Why I am using reference x-axis is because this is the axis where I am going to define the zero of the potential energy. So therefore, let us say that we are going to fix this. So let me write down. So fix this particular level, as zero of the potential energy. So this is the important point. Depending on where you fix the zero level, all your equations will change. It may change from plus to minus also, or it can change expression wise also. So therefore, we are now going to fix this level as the zero of the potential energy. That is what we are going to start like. If you do that, now once this is clear, now we can find out what is the distance of the second mass. Let me simply take the center of mass of this particular mass m2, and from there let me measure what is the distance. So I will now draw this particular arrow. So you know that from here, from this level to this level, whatever that you have, so we will say that this is the length y2, because it is the second mass. We can say that this is y2, and similarly for the first mass, you can also draw a similar diagram or a similar length scale and say that from here to here would be the y1. So y1 means that is for the first mass, 2 for the second mass. And that is one thing. The second thing is already known, which is radius. Let me just emphasize. Please see that there is R here. Capital R represents the radius of the pulley. Why do you want to know the radius of the pulley? Is that we need to know what is the total length of the wire. Here it is written, see. We want to write down an equation for the length of the wire. So if we are going to assume that this is the point A, let me write down that this is the point A and this is the point B. From A to B, what is the distance? We need to know the distance because the wire actually passes through the pulley and then it comes here. So we need the length AB, and the length AB equal to pi into R. 2 pi R is the total circumference. So therefore pi times R will be the radius. Therefore we are going to use that and then write down the equation. So let me go below this particular board. But only thing is that you should remember this diagram. Then only you will be knowing what we are writing. So let me write down here, the length of the wire is given by, total length of the wire will be given by pi R. Pi R will be the length corresponding to the one which is occupying the pulley, plus the length which is connected to the mass m1. Let us say that is y1, plus the length that is connected to the mass y2. So that will be the total length. So I'll say that this is the total length. Now here, when you are writing the total length of the wire, you don't have to worry about whether it is positive value or negative value. So these are the places where you have to pay attention. Okay, certain things like this will look very simple, but it requires a lot of explanation for understanding. And once you understand this, similar ideas can be applied to solving another problem. Okay, we can always solve this problem very quickly within say 2-3 minutes and say that okay, let us go to the next problem. But let me also once again repeat it. Our aim is not to solve many problems very quickly. Okay, suddenly within 2-3 minutes we don't want to finish one problem and go to next one. That can always be done, but that will not serve the purpose of explaining each and every detail that is there in a problem. So therefore, our aim is to explain all the concepts in detail rather than running through several problems. So that is that point, you keep it in mind. And let us now continue that the total length of the wire, why do you want? First thing is, why do you want? This is the equation of constraint. So this is going to serve you the equation of the constraint for a given system, for this particular system. Because this is constraint means restriction. So that means the masses m1 and m2 cannot detach and run away somewhere. That is called constraint. Constraint means you put restriction that the two masses should be tied together and these two fellows has to move together only. That is the masses you don't allow any freedom to move anywhere as it likes. That is the meaning of restriction and constraint. So this equation is going to serve that purpose. Okay, coming to the next important point is that we will have to now write down the kinetic energy and the potential energy. That's what we are going to write down. For potential energy, let me explain now. So that's what we are going to use. You will have to use this is the zero of the potential energy, and therefore what will be the potential energy of the mass m2 second mass? mgh is general formula. So okay, mg is okay into the height will be equal to the negative of y2. That is a place where I want to explain. Minus y2 you will have to substitute. Why it is minus y2 is because this is the 0. So this particular coordinate is 0, 0 origin. This is 0. So anything you measure in the downward direction, that will be a negative value. Therefore, minus y2 will be the length that you will have to use when you are calculating the potential energy. And similarly, when you are writing the potential energy for the mass m1, once again m into g is okay, then multiplied by this y1 should be a negative y1 because we are measuring from this origin. That is important. But that is fine. Now come here. When you are writing down this particular equation, namely the total length of the wire, this idea should not be used. Total length of the wire, you cannot subtract somewhere and add somewhere. Okay, we are interested in total length. Total length is only a scalar, not a vector quantity. So therefore, there you don't have to add. In the case of the potential energy, we need a reference point. Potential energy, by the way, you should once again, let me tell you that it is also scalar. So you are not putting it due to vector. So the minus is not coming because of the vector. That is something that you have to be careful. Okay, minus is not coming because of the vector quantity. That means going in the downward direction. Minus is coming because you have chosen the 0 of the potential energy, that place. That place means as shown in the diagram. Suppose let me draw another, let me arbitrarily draw a pink color line here. So I will show a pink color line here. And suppose this pink color line is the 0 of the potential energy. If I will put if here, if this is the 0 of the potential energy, and then I put a y-axis here and say that this is my origin of the coordinate system, 0, 0, then you have to measure from here to here. This height you have to measure and this height you have to measure. And now in this case, you will be having positive values. So the potential energies will take positive value, not negative value, because this is the 0 of the potential energy. So these are the places where you have to be careful. Your diagram will tell what is positive and what is negative. Okay. So this pink color one you forget. That's why I changed the color. So let us now continue that we have now completed the equation of the constraint is fine. Now let us write down the kinetic energy and the potential energy of the system. Then we can write down the Lagrangian. Now since we have this expression, we are going to use the Lagrangian equal to T minus V, where capital T is the standard symbol for the kinetic energy. Let us write down that this will be equal to half m into the velocity of the first mass, then plus half mass of the second mass, mass of the second mass into V2 square. That will be the kinetic energy part. Then minus the potential energy part will be m into g into, now here you will have to substitute minus y1, then plus second mass gravity into minus y2. That's what we will be writing. But here, as you see, v1 and v2 are coming. So in the last class we have seen we should not use the symbol v. So we will have to convert it into an appropriate coordinate system that we are using. So now what is the symbol that we are going to use is that instead of the v1 square, we will be using y1. y1 is the coordinate we have. Okay, then you take a dot because the time derivative represents the velocity, and then take a square here. That's all. So it is a simple one dimension, therefore it's only one variable. Otherwise you have to write x1 dot square plus y1 dot square plus z1 dot square. Like that you have to write, which we have seen in the last class. Yesterday's class we have seen that. So now it is simple because only one dimension is there. So the variable happens to be y1. That is why we are going to replace like this. And similarly, for the case of the second mass square velocity 2 square, we are going to write down the correspondingly y2, then dot, then you have a square. That's what we are going to substitute. So if you substitute that, we will be having, let us substitute here and write down that the Lagrangian will be equal to half m1 y1 dot square plus half m2 y2 dot square. This particular bracket I am putting only to refresh your memory that kinetic energy terms are over. Otherwise it's only addition, right? For addition and subtraction generally brackets are not required, but this will tell you that okay, kinetic part is over. Now let us go to the potential energy part. Then we will be having minus of minus is there, so that will become plus. We will be writing m1 g y1, then plus m2 g y2. Okay, I think this is fine. And now we have to use the equation of constraint. To simplify. So that means let us write down what is the equation of constraint. The equation of the constraint is pi times the radius of the pulley plus the length y1 plus the length y2. This all of them put together will be equal to the length L, and L is going to be a constant. And if you are going to differentiate this, let us differentiate this. Shall we write here? Differentiate this with respect to time. So you differentiate with respect to time, we will be getting 0 plus y1 dot plus y2 dot equal to 0, because L is a constant. That is why right hand side has become 0. So this gives you that y1 dot will be equal to minus of the y2 dot. Let us have this 1 here, and this one I can have. This is equation number 2, let us have, and this is 3. So now we can simplify. Substitute 2, 3 in 1. So we have the Lagrangian equal to half m1 y1 dot square plus half m2. Again it is y1 dot square. So now you have to see this is also y1 dot square because of equation number 3. It is actually minus y1 dot whole square, so it becomes again plus. So these two terms are over. Then plus the next term would be m1 g y1, then plus m2 g. Here this is the place where we will replace. Y2 will be equal to L minus pi r, then you have a minus y1, and that's all. So this is the simplification that we have done. And now what happens is, this is almost final. I think there is nothing to do here. And what you observe from this equation, how do you know that this is the final required equation that you have simplified? How do you know means, if you look at the Lagrangian now, you have to find out what are the variables available. So what you understand, let me write down here. So from the equation number 4, what we observe is the following. Lagrangian is a function of, what are the variables that are there? You first of all find out which variables are there without dot. Without dot means that is the position. Then you find out how many variables are there with dot, and then you list out everything. So there is a y1, m and g and all you should not consider, they are constant. So variables, let us see, y1. So the y1 is a variable, therefore let us say that Lagrangian is a function of y1, then comma, then come here, L, pi r, all are constant, and again y1 is there. So y1 is enough. Then come in this direction, there is a y1 dot. Once again, there is a same y1 dot is there. Therefore, it is a function of y1 dot. Of course, time is not explicitly present. That is fine. You can in general write down that it is comma t. As I already told you, by writing comma t, there is no compulsion that time has to be present there. Even if it is not there, it is in general a function of time, can be possible. In this particular case, t is not there. You need not write t also. Okay. But however, you already know that there is a time response is going on in an indirect manner. That is why dynamics is taking place. You are basically taking time derivative. So there is an influence of time that happens in the background, but the time is not visible directly in the Lagrangian. That is the only thing. It's not visible in the Lagrangian, but time is there in the dynamics. So our conclusion from 4, or what is that we are observing, is that Lagrangian that we have written down in the equation number 4 is a function of y1 and the corresponding time derivative, and then time. That's all about it. But if you now, this is the place where you have to check now. You do a similar analysis for equation number 1. You have an equation number 1 here. So you can once again ask the question that if I am going to see the equation number 1 and ask the question, what is the Lagrangian function of? Then what is the answer for you? Your answer is like this. Lagrangian is a function of y1. So here it is. Maybe I will write here so that whatever I am speaking should be visible. But I don't want to confuse by writing something here, and therefore I will change the color to the pink color. So now it is in pink color. So it should not disturb the original discussion that we had. Now what is the conclusion from equation number 1 is Lagrangian is a function of, you can see that y1, therefore write y1. Then come here, there is a y2, therefore it is a function of y2, comma is there. Then come in this direction, there is a y2 dot, then there is a y1 dot. So you also write down that there is a y1 dot and there is a y2 dot. So comma, comma, close bracket. So what you observe from the equation 1 is that Lagrangian is a function of y1 comma y2 comma y1 dot comma y2 dot. That is what is the meaning. This particular equation 1. And what is the conclusion and what is the meaning of that's all fine. But what is the meaning of this? This means you have y1 comma y2 and then the corresponding dot. So corresponding dot you don't count. Okay, they are only corresponding time derivative. So how many of them are there without time derivative? y1 and y2. That means 2 variables are there. Since there are 2 variables are there, it means it is supposed to be a 2 degrees of freedom problem. That is what it means. The meaning of this particular analysis, because 2 variables y1 comma y2 are there, this problem should be a 2 degrees of freedom dynamical problem. That is the meaning. But if you are going to come down little bit and see the equation number 4 here, this equation number 4, our conclusion says that this tells you that this is the Lagrangian here. And from this particular Lagrangian, our understanding is that Lagrangian depends on only y, only y1. Afterwards, it is its own corresponding time derivative. That no need to count. Therefore, since only one variable y1 is there, this is actually a 1 degree of freedom problem. So therefore, you have already reduced the 2 degree of freedom problem to the 1 degree of problem because of the constraint. If you didn't use the constraint, you cannot reduce it, and therefore the problem becomes unsolvable. So the point of using the constraint is now clear, because while explaining the theory, I explained what is the purpose of constraint. I said that the purpose of the constraint is to reduce the number of degrees of freedom. That's all I said. But how it is reducing, you may not be able to visualize at that time. Now it is clearly visible in front of you. Therefore, you can always see how you are able to reduce the number of degrees of freedom. Suppose if you say that I don't want to reduce the number of degrees of freedom, then you will have to solve the equation number 1. So this point also again make it clear. If you say that I don't want to use the equation of constraint, then the next question comes, how are you going to solve equation number 1? You can't solve it. So you'll be keeping like that, and then the problem becomes unsolvable, and that is what we say non-holonomic system, non-integrable problem. So you'll be stuck in a situation where problem is unsolvable. So now we will see that this problem becomes simple. This becomes a solvable problem. So you have Lagrangian like this. Let us therefore write down the corresponding Euler-Lagrange equation. So therefore we write the Euler-Lagrange equation for the Lagrangian equation number 4. So that is the step that we are doing. So that means you already know the equation. So this equation every time no need to write, but at least you need to remember what are the derivatives available, then we can calculate those derivatives. So this equation is there. Let me write down for comparing what is required. So this equation tells you that we need to differentiate with respect to q, and we need to differentiate with respect to the q dot. So that is what is required. So let us do the appropriate derivatives. So let me put a line here. So what is the derivative required? Dou L divided by dou Q dot. So I'll write down that dou L divided by dou Q dot. This Q dot, what is the Q dot you have to see? In our problem, this is Y1 dot. So therefore, now you should not write Q dot now. You'll have to write down Y1 dot, because you have already identified what is the exact variable for our problem, and therefore now we can differentiate by looking at equation number 4. So that is quite simple. You now differentiate how much you are going to get, M1 into Y1 dot. That's all right. Plus the second term will give you M2 multiplied by Y1 dot. Then you have a plus. The third term, this particular third term does not contain Y1 dot. Okay, doesn't contain Y1 dot. Therefore, its derivative will be 0. Plus the fourth term does not contain Y1 dot, and therefore derivative will be 0. So that's all over. This derivative is over. Then what is the another derivative that you want? We need dou L by dou Q. So therefore I'll write down, and this is one thing. Second thing is we need dou L by dou Q. And now what is Q? Q is Y1. So dou L by dou Y1 equal to, let us differentiate this. This first term does not contain Y1, and therefore derivative is 0. For same reason, second term also 0. Third term will give you M1 into G. Then the next term will give you plus M2 into G into, you have L. L is a constant, so differentiation 0. Pi r is a constant, 0. Then there is a Y1 is there. For Y1 differentiation will give you a minus 1. And that's all. So that if you simplify, so this gives you M1. There is a minus here, so I'll write down minus M2. Then I'll write down the G here. So therefore, okay, so the Euler-Lagrange equations of motion is so now what is that we are going to see? You understand now. We have to perform a time derivative of this particular first equation, dou L by dou 1 dot. Therefore, we will write down that it is d by dt of m1 y1 double dot m1 y1 single dot plus m2 y1 single dot will be that's all over. Then we have a minus m1 minus m2 times g equal to 0, and that gives you, now you know the time derivative of y1 dot will be y1 double dot, isn't it? Y1 dot is already there. Differentiate once, I will get y1 double dot. So y1 double dot happens to be common. So therefore I will write down here. So y1 double dot is common. So that will be equal to, this one you can take it to the right side. Then we get m1 minus m2, then into g, and divided by, after taking common, we will be having m1 plus m2. And this equation is what is known as the equation of motion. So by the name of the terminology, that should be clear to you. Equation of motion means the differential equation corresponding to the dynamics of a problem. That is the meaning of equation of motion. Equation of motion doesn't tell the solution. So that point should be clear to you. Most of the time, the question paper says that obtain the equation of motion for the system. What is the meaning? The meaning is obtain the differential equation of motion for the dynamics of the system. That's all about it. Writing down or bringing the differential equation or deriving the differential equation of motion, that is the place where you'll have to stop for writing the answer to that problem. There may be another problem saying that solve that particular equation of motion. That is totally a different problem. Solving the equation of motion is another problem. Obtaining the equation of motion is another problem. Okay, you can always combine them and make a continuation and get the solution. But you should be clear about the question, whether you are going to obtain the differential equation and stop there, or given an equation of motion to you, you are going to solve it. Which one you are going to do, that should be clear. So here in the standard thing that you are going to do in the learning of this Lagrangian mechanics is that you'll always obtain the equation of motion, which is known as the Euler-Lagrange equation of motion, and then there you stop. Solution is totally different thing. The solution can be quite lengthy, sometimes too complicated, okay, that you cannot do on a paper and pencil. When situations are complicated, for example, take the case of double pendulum. We have already seen maybe a few lectures back. The solution is not possible. You can't do it on a paper and pencil easily and then generate its solution. So you may have to take the help of a computer to get the solution. So therefore, solving a differential equation itself is a big task. So we are not going to combine that and this. The primary objective of the Lagrangian mechanics part that we are learning is to identify the coordinates of the system, identify the equation of constraint, and then reduce the coordinates to the minimum, so that is known as the degrees of freedom. And once we have the Lagrangian written down for the minimum number of degrees of freedom, apply the Lagrange equation, simplify these derivatives, and then the resulting thing is known as the Euler-Lagrange equation of motion. And that is a place where you will have to stop in general. Okay, most of the time you'll have to stop there, because that is how the question will be there. There may be a quite different question asking for solving a given problem. Okay, that is a completely different problem which we will deal later. Okay, so our conclusion is that this is the answer for this particular system. And now there are some further discussions and details that you need to know. So that's what I am going to explain now. So let me go to the beginning of the board now. This is what we started in the beginning. And then here you see again, now you come back to this Atwood machine, and they say that we can now solve the problem by using or by bringing the concept of the moment of inertia. Here it is there, this mi. So this is the moment of inertia. Okay, so moment of inertia can be brought into the picture while solving, or you can neglect it. You can do both of them. But if you are going to solve a problem against a question paper, they will tell whether you want to use it or not. Explicitly, they will not tell. This is the point where you have to be careful. Explicitly, there won't be printing saying that use moment of inertia. That wording will not be there. By reading the question, you will have to understand whether moment of inertia has to come into picture or not. That decision is where the importance, that is a place where you have to pay attention, and then make sure whether the problem requires the usage of the moment of inertia or not. Now you have to tell, we have not discussed anything about the moment of inertia, and then we got the solution like this. I didn't even mention we will neglect moment of inertia. Okay, I didn't even tell that. So now you will have to think about why the moment of inertia has to come into picture in this problem, and if at all it is coming into picture, what is the place of relevance in this Atwood machine moment of inertia? Where is the place of reference or connection? What connection is there in this? That is what we are going to discuss. It is a simple thing, but you'll have to be careful in understanding this particular point. Now what is this one? This is the pulley that you are going to have. I think this color is not good. I'll take some other color. So this particular pulley that you have, the pulley can be something like a circular disc. It's possible you can have a circular disc. Disc means something like, you have a 5 rupee coin. It's a solid disc everywhere. Otherwise, it can be a hollow one. Hollow one means something like a circular ring. It can be anything of that. So that is why we say that something like a hoop or a ring, for example. So the detail of the pulley means whether the pulley is a solid material like a disc, or it is looking like a hoop, or it is a ring. What it is, what kind of object is that pulley? That's the first point. And second point is, we also need to know what is the mass of the pulley. What is given for the time being, what we have taken is only the radius of the pulley. We didn't discuss anything about the mass of the pulley, or we didn't even think about it. Okay, this particular pulley is fixed. This is another important point you have to remember, that this particular pulley is fixed in one place. Pulley itself will not run away to another place. It is fixed at this particular point, which means that the pulley can rotate like this. It can revolve either in the clockwise direction or in the anti-clockwise direction, depending on the masses M1 and M2. That is the only thing that is allowed, but the pulley itself will not translate from one place to another place. That is called a fixed pulley. So now it is clear where is the moment of inertia coming into picture. Whenever a solid object is rotating or revolving about an axis, moment of inertia has to come into picture. Okay, such wordings will not be there explicitly in the question paper. Use the moment of inertia and do the calculation. Like that, nothing will be written. But you'll have to understand that whenever a massive object which has a particular shape is very important. Shape means whether it is taking the shape of the disc or a hoop or a ring or a rod or a spear. Okay, or any other arbitrary shape. That shape, once the shape is coming into picture, and once you know the mass of the object, which is not zero, that is why I say massive object. If it is the case, moment of inertia has to be inserted into the calculation. You have to use. Now, we have not used in our calculation for the time being. It means that we have made an indirect assumption. We ourselves made an assumption, but we did not explicitly tell. What is the assumption is that the pulley is massless. That's the only option. You can't say that the moment of inertia itself is not there. We can only say that if the mass of the pulley is too little, then mr square approximately. Okay, mr square is a typical expression that we will be using. It may be 1/2 mr square. If you are using disk, it is 1/2 mr square. If it is something like a ring, then it is just m into r square. So in any case, radius is not zero, but how can it go to zero? Moment of inertia can go to zero only if the mass of the pulley is approaching zero. It cannot be zero. Practically, zero is not possible. So we can only make a situation where the mass of the pulley is negligible. That is the only situation where we can neglect the moment of inertia. Okay, otherwise means in most of the practical situation, such assumption of making mass of the pulley zero is not a good idea, and therefore we will have to insert the moment of inertia into our calculation. So this is the point that should be clear, which means that you yourself think and then generate the idea and then decide. The decision is yours. You decide whether the moment of inertia is going to be inserted into the system or not. And now if you are going to make a decision that, okay, I am going to insert the moment of inertia into my calculation, then where you will leave insert. So in this equation, now you'll have to come to this particular equation, and this is the starting point. This is how your starting point. And if at all you want to insert the moment of inertia, we can now write down that the moment of inertia of a disk, for example, let us assume that it is a disk, okay, not a hoop, then this is equal to I, and that will be equal to mr square by 2, where capital M will be the mass of the disk, capital R is already there, so that is not a problem. So this expression mr square by 2 has to be inserted. Where will you insert? So moment of inertia will be coming into only kinetic energy term. Moment of inertia will not enter into potential energy term, right? That is known to you. And therefore, what is the kinetic energy due to the rotation of the disk? That is the expression that you need to know, and then add it. So how will you add? Now let me add this. So here I'll put a plus and then add. Whenever an object is rotated, that is a solid object is rotating with a moment of inertia I with an angular velocity omega, then half I omega square will be the kinetic energy due to rotation. So now it is clear that the total kinetic energy of the system will be equal to kinetic energy of the mass 1, mass 2, and the rotational kinetic energy of the disk or the pulley. Pulley is what is rotating now. So that should be added. This is the place where the change has to be incorporated. And then in place of the I, here you have I, right? In place of the I, this expression has to be used. This one you have to use it here and then put it in this particular place. But that is not the only thing. There is another difficulty. The next question is, what is omega and how will it perform the differentiation? So that should be clear, right? So only if it is clear, you can now simplify equation 1, 2, 3, etc. So it is not complicated, but it is a very simple thing. You need to know. That part I will explain now. Okay. So if you are going to use, let me put a just line here. Let us not do the repeated calculation. I will only explain what to be done with this I. So if you are going to have I equal to mr square by 2, that is fine. This is one thing. And our main objective is the insertion of the kinetic energy. So we will be having a term which is equal to half I omega square. That is the term that you are going to add. So we will have to simplify only this term. That's all. All other things you have already simplified. So let us do that. It is 1 by 2 into I into omega is nothing but theta dot. Why we are writing theta dot, you already know. In Lagrangian dynamics, everything should be written in undotted version and dotted version. So therefore, omega and all should not come. Therefore, if theta is one variable, then we say that theta dot will be the corresponding dotted variable, then I into theta dot square. But now the question is, can the theta stay as an independent variable or not? So this is the place where the crucial thinking comes. And theta cannot be independent of the dynamics that is happening. Okay. Theta dot means what? Angular velocity. So how fast? So when this particular wire or thread that is going like this, and then it crosses the pulley and then comes down, right? So actually what is moving here is the wire itself is moving and coming like this. So when that comes like this particular pulley is making a rotation. So what is very crucial is that this pulley has to rotate according to the wishes of the wire. The wire has to decide what is the speed. Pulley itself will not rotate on its own speed and then the wire will go on its own speed. That is not at all possible. That is a place where the constraint comes into picture. This is called constraint. Okay. Pulley has to rotate without any freedom. What is the way in which it will rotate is, it has to rotate according to the wishes of the wire that is going in this at this particular speed. Okay, therefore, if you take any point on this pulley and draw a tangent to that, this is the tangent to the pulley at this particular point. This is the point. So when you draw a circle like this and put one point here, what is the tangent mean? This is the tangent, right? That is the tangent. So when a pulley is coming like this and then turning like this, and then when it is coming like this is the point where you draw the tangent. Why do you want to know the tangent is, then we know the tangential velocity. Tangential velocity means you draw the tangent and ask the question, what is the linear velocity at that point? Tangential velocity is linear velocity. So linear velocity equal to r into omega for a circular motion. That is what we are going to use. And then if you say that v equal to r omega, now I can say that this becomes r into theta dot. That is what is the meaning. But the problem is, okay, but we are now having v equal to r into theta dot is fine. but we don't have v in our problem. You know that v is the velocity of what? Velocity of this wire. This wire is moving, right? So at what speed this velocity will be there is y1 dot will be the speed of the wire. With that speed only the wire will go up, and therefore v should represent y1 dot. That will be equal to r times theta dot. So what happened? This is very important. So what happened is very important. Our conclusion is therefore theta dot can be rewritten as y1 dot divided by r. This equation tells very important information. The information that you are going to get is that the angular velocity of the pulley depends on the speed at which the masses are moving. Y1 dot represents the speed of the mass, right? Ultimately, speed of the wire means what? The mass is coming up or mass is coming down. So whatever be the speed of the mass, that will be the speed of the wire that is crossing this pulley, and therefore the angular velocity of the pulley itself will be depending on that, and therefore it cannot be an independent variable. So our conclusion is very important conclusion that theta dot is not an independent variable. Not an independent variable. So what is the meaning? Our meaning is that the number of degrees of freedom did not increase. Okay, we have already solved a problem. We have already solved a problem, and we have already decided what is our decision. That again, this board is disappearing. Again, I'll go back. So somehow this board is not easily going. Oh, okay, no. Fine. Already we have decided that this is a 1 degree of freedom problem. Now the question comes, because of theta dot, will it become 2 degree of freedom problem? Will it become a higher dimensional problem? That is what is the doubt that we had. But this equation tells clearly that theta dot cannot be an additional degrees of freedom. It cannot be, because of the equality here. Theta 1 dot is related to y1 dot, means it cannot be an independent variable. Therefore, our problem still remains as one dimensional problem. So even after including the moment of inertia into the system, it is a one dimensional problem, and therefore we can solve the problem easily, which means that now next what to be done, that is quite clear to you. You take this particular theta dot and then substitute here. So here you'll have to substitute. Okay, over. Then after that, what will you do? You take this particular expression and then insert into the Lagrangian. Okay, and then this particular expression insert into the Lagrangian, and then again you perform the appropriate derivatives like dou L by dou Q, etc., and then get the answer. Now there will be a small change in the answer, of course. So there will be a small change in the answer. Probably instead of repeating the calculation, there is nothing big to repeat the calculation. So therefore, I will better write down what is the small change that you will get. You will be getting this answer, y double dot equal to m1 minus m2 divided by, same thing I am writing, you see. Then here you have m1 plus m2, and plus I will be getting I divided by r square. That's all. So this multiplied by g, that's all. So this will be the new answer that we will be having if you are going to include the moment of inertia into the system. So that will be the conclusion, and it is not difficult because I already explained where to insert all the expressions, and if you do that, you can easily verify, at least you verify whether you are able to get this expression. It's a very simple one. So this is the answer. So now what is the conclusion that we see is, even though we have taken only one example, the time is now getting over. Our conclusion is that the explanation gives you where is the difficulty coming into picture, how you have to think. Okay, where is the simplification that you have to focus your attention, and these things are very important. And once the methodology is clear, you will have to use similar ideas when you are trying to solve another problem. Maybe in the next class we will continue another problem, so that you will be knowing a different kind of constraint, because constraint is the place where difficulties come. Different constraints will pose different problems to you, so you must be able to tackle these situations. So in the next class we will continue with solving another problem. Okay.